Hello, everybody. Welcome to the first lecture for the Physics 222 class, spring of 2020 here. So again, as described in the syllabus, take a look at the syllabus, but what I'm planning on doing is doing these video lectures, posting them to the YouTube channel. In the future, I might get them posted into Canvas as well, but we will meet using Zoom at the regular scheduled class time. And that will be kind of a time to answer questions. Maybe I'll talk a little more about the material, but mainly that I guess is kind of used as an office hour sort of thing, whereas the lectures will be recorded here. So today I want to talk about Newton's universal law of gravitation, right? And this can be found in the e-textbook, Halliday and Resnick on Wiley Plus, in chapter 13, and today I'm talking just about sections 1, 2, and 3. If you prefer to read the OpenStax textbook, I mean, it's got the exact same material. You can also go to chapter 13 of the OpenStax Volume 1 textbook, sections 1, 2, and 3, and you'll find the exact same material. So I don't care which one you read, but you should read something about it and watch these videos. And then what you'll have is a reading quiz in Wiley Plus over the material that I talk about and that's in those sections. For this chapter 13, gravitation, I'm not going to assign any homework problems. Typically, though, most chapters I'll assign homework that you'll also do in Wiley Plus. For instructions on how to connect to the Wiley Plus, go look at the syllabus. There are instructions there. But for now, I want to get onto the topic at hand here, Newton's law of universal gravitation. And one thing I'm going to do as well here is I have a document camera that I'm going to try to share with you so you can see what I'm writing. So I'm going to actually write out the equations here. So let's go ahead and try this. Hopefully this will work well. So first of all, before I talk about Newton's law of universal gravitation, I need to talk or remind you of Newton's laws, because what we're talking about is a force due to gravity. That's what we mean by Newton's law of universal gravitation. So just remember from Physics 221, Newton's first law, right? You need a force to cause an acceleration. And Newton's second law says that if you add up the forces you have acting on a mass, they have to equal the mass times the acceleration of the object, right? And so this is the second law. There's also the third law, which we'll talk about here in a moment as well. Right? Basically, it says if I push on something, that something has to push back with an equal and opposite force. So first of all, let's talk about the force due to gravity between two objects. Which is what Newton's law of universal gravitation describes. And there are two aspects, of course, to any force. Since forces are vectors, they have to have a direction and a magnitude. So Newton's law of universal gravitation has to describe both of those things. So first of all, let's talk about the direction of this gravitational force, right? And so we're talking about the force between two masses, say M1 and M2. So maybe mass 1 is the Earth and mass 2 is the moon. Or it could be mass 1 is me and mass 2 is the desk. The idea that it's a universal law means that it works for any two masses, no matter what they are, right? Now, we'll also have a distance between the masses. And it turns out that in the universal law, you can consider any big spherical object like the Earth, when you're calculating this force, to be that all the mass is at the center, right? So here what we're looking at is the distance between the two centers of mass of the objects. We're going to call that R. Right, we're going to treat them like point masses at those points, at their centers. Now, the direction of the force is pretty easy. Newton's law of universal gravitation says that gravity is always attractive. So any two masses want to attract one another, right? So M1 is going to pull to the left on M2, right? It's going to attract it. Now, according to Newton's third law, if I'm pulling that way on M2, M2 has to pull back in the opposite direction, but with the same force, right? So that's a consequence of Newton's third law. But we can always tell the force, the direction of the force, just because it's an attractive force. Now, the next thing we want to talk about is the magnitude of the force. How do I actually calculate the number of newtons, right? And what I think Newton did, or well, it's kind of maybe a historical story. He came up with a formula to calculate this force. And what I'm going to do is write the formula down. How did he come up with this formula? Right, well, just briefly, a little bit of history. Back in the 1500s, there was an astronomer named Tycho Brahe who had made very meticulous observations of the planets and their orbits. Right? He filled up tables of numbers of where those planets were in the sky. His student, Johannes Kepler, spent many years studying that data and finally came to the conclusion that the orbits of the planets were ellipses. He could describe them mathematically as ellipses. So basically, I think what Newton was looking for was a force that he could use in his second law to calculate the acceleration of the planets, and then from that acceleration, go back and calculate that orbit, right, where the planet is. And as it turns out, he came up with an expression or a force law that does just that. If you use it, you will get ellipses for the orbits of the planets. And so he knew that he was right. So let's write down the force law. So the force between any two masses, M1 and M2, is given by this. There's a proportionality constant. I'll write that here in a second. But the force is proportional to the product of the two masses, right? M1 times M2, and inversely proportional to the square of the distance between those masses. Now, the proportionality constant, I'm going to write out the value, is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. That's a really, really tiny number. And this is what really makes gravity such a weak force. Right? You end up needing a lot of mass, like the entire mass of the Earth, just to pull you toward it. It's also why, right, you don't see the desk and myself attracting or moving toward one another. The force is so weak that I can't really get it to overcome friction between the desk and the floor very easily. So gravity is a very, very tiny force due to this constant. Now, how do I know what that constant is? Well, one way would be to calculate those orbits, those elliptical orbits, right? And you get an ellipse, but you might have to adjust, the parameters of the ellipse to fit the Earth's orbit, or Mars's orbit, or Jupiter's orbit. And what you find, though, is you get a number that works every time. And this proportionality constant is a universal constant that does not change, right, anytime you use Newton's law of gravitation. So a couple other things to point out here about Newton's law. There's an r squared in the bottom. We call this type of force an inverse square force, or this law, an inverse square law. So one of the types of questions you might see in a reading quiz, for example, is, let's say I double the distance, right? So I take my two masses and I go to twice the distance. So basically what I'm doing there is saying r is going to 2r. What happens to the force in that case? Well, let's use our universal law of gravitation here and just plug in 2r, right? Assuming all the masses are the same, g is always the same. I've just doubled my distance. Now when I square it, you'll see I get a factor of 4 here. This becomes g m1 m2 over 4r squared. So what happens is when you double the distance, you actually reduce the strength of the force by 1/4. Maybe you can see, what if I tripled the distance? I made this 3r, right? I'd get a 9 here. And so the force reduces by a factor of 1/9. So this is what I mean by an inverse square law, right? The force gets weaker as the square of the distance. And so it goes fairly quickly, it gets weaker fairly quickly due to that 1/r² dependence that it has. You could also see questions about, well, what if I change the mass? What if I double the mass, just m1? Well, then the force would double. What if I doubled both masses? Well, then the force would quadruple, right? Because I'd have 2 times 2 there. Now, you'll see those kinds of questions in the reading quiz that you'll find on Wiley Plus. Sorry, that's my dog. So you'll see those kind of questions just about the nature of the force. Now, again, I'm not going to assign homework problems from this chapter for a couple reasons. First of all, the main reason is that we'll see very similar problems when we go to electricity. Turns out the force law for electric charges is very similar to Newton's universal law of gravitation. It will have a different constant is one of the main differences. But you will see questions on the reading quiz. Now, one last thing I do want to point out here, we did have a G that we used last term, right? We talked about acceleration due to gravity, and we used a little g for that. And we always used g is equal to 9.8 meters per second squared. So how does that relate to the capital G, or to Newton's law of universal gravitation? Well, remember, what I mean by the acceleration due to gravity is I'm near the Earth, and my weight is equal to mg. Right? M little g, my mass times the acceleration due to gravity. Now this weight is the gravitational force from the Earth pulling down on me. So it should equal this expression, right? But what masses do I use? Well, first of all, the two masses that are attracting one another are me, my mass, and then the whole mass of the Earth that I'm standing on. So I have an ME here, mass of the Earth, right there. Now, again, like I said before, I can treat the mass of the Earth as if it's all at the center here of the Earth, as far as calculating force due to gravity. So I'm going to use the radius of the Earth squared. Now my mass will cancel out, and I can see that the acceleration due to gravity depends on the mass of the Earth and the radius of the Earth. So this acceleration due to gravity is not the same all the time. It will depend on what planet you're on, right? So you go to Mars, you'd have to plug in the mass of Mars and the radius of Mars to get the acceleration there. Also, it explains why the acceleration of gravity is a little bit different at sea level. For example, it's about 9.81. In Klamath Falls, we're at about an elevation of about 4,000 feet or so. It's about 9.79. Right? It's different because we're at different distances from the center of the Earth. We're at a bigger elevation, or R is a little bigger here in Klamath Falls. So the acceleration due to gravity can change, whereas G, the capital G, universal gravitational constant, does not change. It is a universal constant. So for right now, that's what I wanted to talk about in this lecture about Newton's law of universal gravitation. One thing that you could do with this is talk about the energy, right? Anytime you have a force that we can write an expression for like this, we should be able to define a potential energy. I'm not really going to ask a lot of questions about that in the reading quiz or the homework. We will see very similar things again when we go to electricity. For this lecture, I just wanted to introduce you and kind of show you Newton's law of gravity to kind of fill out what we did last term. But you'll also see it is very similar to what we're going to do with electricity. With electricity, we just have a different force law. It turns out actually to be pretty similar. But what I'm going to do is, in the next lecture, a separate lecture, I'm going to talk about energy and what is the potential energy due to gravity, right? If you're the moon or you're a satellite out in the orbiting the Earth or something like that. But for this lecture, we'll just do that. Again, you might see questions on the reading quiz concerning this stuff. So I'm going to stop there for this lecture and look for the next one. Thank you.